Dear students, in this video, I will be discussing one of the important rearrangement reactions in organic chemistry, the Baeyer-Villiger rearrangement with their mechanism. For this purpose, I will be taking 10 important examples in Baeyer-Villiger rearrangement and discuss their mechanism in detail. Okay, you know the treatment of a ketone, both aromatic or aliphatic, with a peracids such as peracetic acid or perbenzoic acid or metachloroperbenzoic acid gives a carboxylic ester by insertion of oxygen. That is, the treatment of a ketone with a peracid such as peracetic acid or perbenzoic acid or metachloroperbenzoic acid gives a carboxylic acid by the insertion of oxygen, and hence Baeyer-Villiger rearrangement is often termed as Baeyer-Villiger oxidation. Baeyer-Villiger oxidation. These are the 10 examples I am going to discuss here. See these examples, and I will take each of these examples one by one and discussing their mechanism in detail. Okay, see, it is the first example, a ketone on treating with the trifluoroacetic acid, trifluoroparacetic acid, forming an ester, corresponding ester. How this will be converted to an ester, it can be discussed. You know, the reaction of Baeyer-Villiger oxidation usually takes place by a concerted intramolecular process involving the migration of a group from carbon to an electron deficient oxygen, possibly by the way of a cyclic transition state. See, first of all, the trifluoroacetic acid donates a proton to this oxygen, and the peracetate anion attached to this positively charged carbon atom formed after the transfer of Y electron to this oxygen. Thereby, you will get this compound. Okay, then you can see the alkyl shift to the electron deficient oxygen, and then this bond gets broken and the carbonyl group thereby abstract a proton from this OH group, and rearrangement takes place forming this ester. It is the mechanism of Baeyer-Villiger rearrangement, the general mechanism. For this reaction, we will get this ester by the Baeyer-Villiger oxidation reaction. You can see, first of all, peracetic acid, here it is trifluoroperacetic acid, donates a proton to this oxygen, and thereby the peracetate anion attached to this electron deficient carbon atom, forming this molecule, and then alkyl shift takes place to the electron deficient carbon atom, whereby this rearrangement takes place. This carbonyl group abstract proton from this OH group, thereby this becomes the new carbonyl group, and the alkyl group shifted to this oxygen, thereby this ester is formed. That is the mechanism in this reaction. It is the general mechanism of Baeyer-Villiger oxidation reaction. Then in the second case, see, it is the ketone. It is an unsymmetrical ketone. Here it is a tertiary butyl group. It is an alkyl or phenyl group. It may be an alkyl or phenyl group. It is tertiary butyl group. It is an unsymmetrical ketone also. How the Baeyer-Villiger oxidation takes place in unsymmetrical oxidation? I mean unsymmetrical ketone, that can be seen. First of all, as in the previous case, the perfluoroacetic acid, in this case also perfluoroacetic acid can be used. Thereby this, as in the previous case, this molecule is formed, and alkyl group. Here there is a competition between this alkyl group and this alkyl group. This R group is actually a primary alkyl or phenyl group, and it is a tertiary butyl group. When this ketone is unsymmetrical, you know, the migratory aptitude of these two alkyl groups or aryl groups matters. In this case, R group is a primary alkyl group or a phenyl group, and this is the tertiary butyl group. Here, the migratory aptitude of tertiary butyl anion to this electron deficient oxygen is greater than the primary alkyl group or phenyl group. Thereby, this tertiary butyl group migrates from this position to oxygen. You can see the rearrangement reaction. Here, this migrates to oxygen. Thereby, this bond gets broken to form a double bond between this carbon and oxygen. Thereby, this pi electron gets shifted towards this oxygen, and this oxygen capture a proton from here. Thereby, this reaction takes place, forming the ultimate product through the transition state. This transition state is often named as Crick's transition state, and by this rearrangement we will get this molecule. It is the ester. Here, one of the important aspect of this rearrangement is when the ketone is unsymmetrical, migratory aptitude, the alkyl or aryl shift takes place by the migratory aptitude. Those groups which having high migratory aptitude will migrate to the electron deficient oxygen atom. In this case, when the R group is an alkyl or a primary alkyl or a phenyl group, then this group which having greater migratory aptitude than the primary alkyl or aryl group shifts to the oxygen atom, forming the required product, that is the ester having this structure. Okay, that is the second case. Then if you take the third example, you can see it is the third example when this ketone also is an unsymmetrical ketone, where here this R group is a primary alkyl group, it is phenyl group, aromatic group. When it is treated with the trifluoroparasitic acid, as in the previous case, first of all, a proton is captured by this oxygen, followed by the trifluoroparasitate ion gets attached to this electron deficient carbon atom, forming this molecule. You can see this molecule. Here, this proton is captured by oxygen, and the trifluoroparasitate ion is attached to this electron deficient carbon atom, whereby formed. Thereby, this molecule is formed. Then, here is a competition between this R group, which is a primary alkyl group, and it is the phenyl group, aromatic group. The migratory aptitude of phenyl group is greater than R group. Thereby, this phenyl group migrates. You can see the migration like this. The pi electron shifts towards oxygen. Thereby, the bond between oxygen and oxygen gets captured, broken. Then, the double bond, the pi electron between the carbon and oxygen shifts to the oxygen, and the oxygen capture a proton from this OH group. Thereby, the product is formed like this through this transition state, a cyclic transition state. Here, the trifluoroacetate ion is eliminated, forming this product. You can see the proton is eliminated, this bond gets broken, forming the ultimate product. It is the ester. Okay, that is how this reaction follows. One of the important aspects it is in this reaction is it is an unsymmetrical ketone. Okay, when the R group is primary alkyl and it is the phenyl or aryl group having greater migratory aptitude, it will migrate to the electron deficient oxygen atom, as in this case. Okay, you know the migratory aptitude of the alkyl or aryl group is like this. Alkoxyalkyl greater than tertiary alkyl, greater than cyclohexyl, greater than secondary alkyl, greater than benzyl group, greater than phenyl group, greater than vinyl group. It is in turn greater than primary alkyl group. Then comes cyclopropyl group, then methyl group, and hydrogen. Hydrogen has the least migratory aptitude. Among the aryl group, if it is substituted, you know, the migratory aptitude is like this. Methoxylphenyl, paramethoxylphenyl, then paratoluene, then comes phenyl, and then parachlorophenyl. That indicates as the electron withdrawing group is attached to a benzene ring, it has the lesser migratory aptitude. Then comes to the next example, the fourth example. It is the fourth example. It is a bicyclic compound. In the case of cyclic ketone, usually a lactone is produced. Cyclic ester, lactone is produced. For example, in this molecule, if this molecule is treated with peracetic acid, then as in the previous case, first of all, the proton is captured by this oxygen by shifting the pi electron towards this oxygen. This oxygen captures this proton from peracetic acid, and the peracetate ion will be attached to this electron deficient carbon atom. That is the first step. You can see thereby we will get this molecule. Then in the next step, the alkyl group gets migrated. This alkyl group is migrated towards this oxygen, and then rearrangement takes place to form the final product. You can see the mechanism. Here this alkyl group first migrate towards this oxygen, thereby this bond gets broken, and this acetate ion capture this proton, whereby this bond gets shifted here, thereby a keto group is produced between this carbon and the oxygen, and hence you can see this lactone is produced by the removal of acetic acid. Acetic acid is removed and this cyclic ester lactone is produced. See the next example. Here hydrogen peroxide, usually in presence of a base, is used instead of per acid. We can use hydrogen peroxide in presence of a base. For example, in this cyclic ketone, first of all, hydrogen peroxide, a hydrogen atom from hydrogen peroxide is captured by this oxygen as in the previous case, and then alkyl shift takes place. Then rearrangement takes place to form the product. That is the usual procedure or the usual mechanistic pathway. First of all, a proton is captured by the carbonyl group, and the peracetate or peracid anion is attached to the electron deficient carbon atom. Then rearrangement takes place. You can see the example. It is the molecule formed by the capture of this proton and the attachment of anion to this carbon atom, and then the alkyl shift. You can see the alkyl shift here. This alkyl group shifted to this oxygen, then this electron shifted to this oxygen. Then you can see this proton is captured by this oxygen, whereby a double bond is formed here. Then this lactone is produced with the elimination of water. That is the mechanism of this Baeyer-Villiger oxidation reaction. And the next example, the sixth example, you can see here is a nitrophenyl group and here is phenyl group. It is an unsymmetrical ketone. It is phenyl group, it is nitrophenyl group. In presence of peracetic acid, Baeyer-Villiger oxidation takes place. See how the mechanism going on. See, as in the previous case, the carbonyl group first capture a proton from this paracid, trifluoroacetic acid, and the trifluoroparacetate ion is attached to this electron deficient carbon atom, thereby forming this molecule. Then the migration of alkyl or aryl group. You can see here is a phenyl group and it is nitrophenyl group. Because of the presence of this nitro group, it is an electron withdrawing group at the para position of this phenyl group. Then this phenyl group, compared to on comparing the migratory aptitude, phenyl group will be having greater migratory group than the phenyl group with the electron withdrawing group, the para-nitrophenyl group. Thereby, phenyl group will migrate towards oxygen atom. You can see the migration. Then, as in the previous case, electron shifts takes place, thereby producing the product with the elimination of trifluoroacetic acid. It is the product. This can be represented like this. Okay, this is the product of this Baeyer-Villiger rearrangement reaction. Okay, this seventh example, you can see this ketone. It is an unsymmetrical ketone, methoxyphenyl group, and here it is phenyl group, so it is unsymmetrical ketone. When it is treated with the trifluoroparacetic acid, Baeyer-Villiger rearrangement takes place. As we have discussed, the mechanism goes through by the absorption of a proton first by this carbonyl group, and the trifluoroparacetate ion will be attached to this electron deficient carbon atom. Then the aryl group, here the phenyl or methoxyphenyl, which group should migrate depends on the migratory aptitude. You know, the migratory aptitude of methoxyphenyl group is greater than phenyl group, because this methoxy group, which having plus M effect, having greater migratory aptitude than this phenyl group. See the mechanism of the reaction. First of all, this molecule is formed by the abstraction of proton and the attachment of trifluoroparacetic acetate ion to this carbon atom, and then migration of methoxyphenyl group takes place like this, whereby bond shifting takes place like this. Here trifluoroacetic acid, trifluoroacetic acid is eliminated, forming the product. You know, the structure of the ester formed by this Baeyer-Villiger rearrangement is like this. This can be represented as this. Okay, the next rearrangement reaction, that is the eighth example. You can see it is also an unsymmetrical ketone. Here it is methoxyphenyl, whereas it is nitrophenyl, para-nitrophenyl. This is para-methoxyphenyl. And so this is an unsymmetrical ketone. You know, para-nitrophenyl group having this nitro group with the minus M effect, whereas this methoxy group having plus M effect. Usually this group, the migratory aptitude of this group, the para-methoxyphenyl group, will be greater than the para-nitrophenyl group with this minus M group at the para position. And the mechanism is similar to the other mechanism we have already discussed. First of all, the proton captured by this carbonyl group and the trifluoroparacetate ion is attached to this electron deficient carbon atom. Then migration of the para-methoxyphenyl, which having greater migratory aptitude, will take place, and the rearrangement takes place to form the product. You can see the mechanism. It is the first compound obtained, then molecular rearrangement. the shifting of para-methoxyphenyl group towards this electron deficient oxygen, then proton captured by this trifluoroacetate ion to eliminate trifluoroacetic acid, forming the product having structure like this. It is the ester of this by this Baeyer-Villiger oxidation reaction. Okay, see this example. It is a cyclic diketone. Cyclic diketone. Cyclic diketone usually gives an anhydride, cyclic anhydride on Baeyer-Villiger rearrangement reaction. For example, this cyclic ketone, cyclic diketone, on treating with metachloroperbenzoic acid. As in the previous case, the mechanism follows through the absorption of a proton from this metachloroperbenzoic acid by this carbonyl group, followed by the attachment of the residual anion to this electron deficient carbon atom to form this molecule. And then next, the rearrangement or shifting of this alkyl group towards this oxygen. You can see the shifting of this alkyl group to this oxygen, whereby bond rupture takes place with the elimination of metachlorobenzoate ion. This metachlorobenzoate ion capture this proton, thereby metachlorobenzoic acid molecule is eliminated to form the anhydride with this structure. This can be represented like this. It is the cyclic anhydride formed from this diketone by Baeyer-Villiger oxidation reaction. The next, the last example, see this example. It is a cyclic ketone on treating with metachloroperbenzoic acid. Metachloroperbenzoic acid. Then the Baeyer-Villiger rearrangement takes place as in the previous case. First of all, proton capture takes place from the metachloroperbenzoic acid along with the attachment of perbenzoate anion to this electron deficient carbon atom to form this intermediate molecule. Then this molecule, from this molecule, alkyl shift takes place as in the previous case. Here this alkyl group shifted to this oxygen, whereby this bond rupture takes place with the elimination of metachlorobenzoate ion, and this metachlorobenzoate ion capture this proton, forming the product having this structure. It is the ester, lactone, so formed from this ketone, cyclic ketone by Baeyer-Villiger rearrangement reaction. Okay, we have already discussed in detail 10 important Baeyer-Villiger rearrangement reaction with their mechanism. I hereby conclude my video. If you like this video, please share, and if you have not yet subscribed this channel, please subscribe. Thank you for watching. Thank you.